It's a really great pleasure to be here at Mary. And this work today is sort of a double affiliation between McGill, which is where I did my PhD, and my current affiliation in Oldenburg, where I continue some of that work. And today I'm going to talk about both aspects. So I'm really glad to be allowed to talk about timbre, and Dan invited me, saying he also waded through the mess of timbre in his PhD. So originally I thought, oh, that's a cool title for a talk, wading the mess of timbre, but I thought I'd keep it more scientific, although the content is the same actually. Some advertisement. It's timbre high noon. This year, we started the year with a really nice workshop on timbre in Berlin. And the next year is going to be even better with an upcoming Springer Handbook of Auditory Research volume, which features some of the speakers of the Berlin workshop, as well as a timbre workshop at McGill University in summer 2018, and that's even going to be bigger than the Berlin workshop, so that's really nice. Okay, and you find all the workshop talks here at this link. Okay, so let's just jump right into 150 years of timbre research. It all started, of course, with Hermann von Helmholtz and his classic view, which is still quite dominant today, which basically considers timbre as the relative amplitude of the partial tones and basically discards any phase information. And then modern timbre spaces or approaches to timbre research have taken a slightly different approach and first started with dissimilarity rating studies, and then constructed by using multidimensional scaling, sort of geometric representations of the used stimuli in these studies, and then the position of the stimuli along the dimensions of the obtained spaces is usually interpreted in terms of acoustic features. So one classic timbre study, timbre space study from McAdams in '95, for example, shows that dissimilarity ratings can be well described by one dimension, which corresponds to the spectral flux, so it's spectral centroid, which is the center of gravity of the spectrum. Another dimension corresponds to the attack time of sounds, and the third dimension corresponds to spectral flux. And then more contemporary approaches have taken sort of more high-dimensional approaches to describing the acoustic basis of timbre, and this includes work by Elliott and others, and Patil and Munya El-Hilali have done great work on that, as well as Etienne Touré recently. So these are kind of very coarse pillars of timbre research and underlying acoustics of that. At the same time, defining timbre has always been sort of a problem, and here's the infamous ANSI definition: timbre, that attribute of auditory sensation which enables the listener to judge that two non-identical sounds similarly presented, having the same loudness and pitch, are dissimilar. And then they add a great note: timbre depends on the frequency spectrum, also depends on the sound pressure and the temporal characteristics of the sound. So it's really highly concrete. In a response to that, Bregman noted, this is of course no definition at all. The problem with timbre is that it's the name for an ill-defined wastebasket category. I think the definition should be this: we don't know how to define timbre, but it's not loudness, it's not pitch, and we need a better vocabulary concerning timbre. And then, fully radicalized at the end of his PhD thesis, Keith Benner-Martin noted timbre is empty of scientific meaning and should be expunged from the vocabulary of being science. Otherwise, great thesis. So, what I'd like to convince you of today is that we don't have to become too desperate about the notion of timbre. That's my proposal. The notion itself is perhaps somewhat vague, perhaps an umbrella term, but if we specify what we mean by timbre and more importantly which aspect of timbre we're studying, then we probably don't get into too much trouble. At least that's what I hope to convince you of. So here are 4 distinctions that I'd like to make on timbre. First, it is a perceptual attribute. Second, it's a quality and a contributor to source identity. Third, it's a property of fused auditory events. And fourthly, it functions on different scales of detail. And the structure of my talk will be, I will go through these distinctions, and I will start with a few conceptual remarks, which then I'll try to support by some empirical work. Sometimes the empirical work does not really support it, but at least should somehow fit conceptually into these distinctions. Okay. So first, timbre is a perceptual attribute. This might even be slightly controversial in an engineering school. If you tell this to psychologists, they'll say, yes, of course, and what else? But in kind of neighboring disciplines, especially MIR and also music theory and composition, people sometimes use the notion of timbre in a way that does not primarily refer to perceptual phenomena. So for instance, Curtis Rhodes writes in 2015, the ANSI definition describes timbre as a perceptual phenomenon, not as an attribute of a physical sound. Despite this, everyone has an intuitive sense of timbre as an attribute of a sound like pitch or loudness, Coltrane's saxophone sound, for example. From a compositional point of view, we are interested in the physical nature of timbre. And then there are some some weird curves that are hard to understand. In order to manipulate it for aesthetic purposes, the anachronistic term timbre will likely be preceded by a more precise taxonomy in scientific discourse, but then in electronic music it seems to be unavoidable. So for me this seems it's not really easy to understand, because on the one hand it's supposed to be central in electronic music, but for say scientific discourse or for psychology it's unsuited, so it's not straightforward. Furthermore, it tries to reinterpret a lot of history on the psychophysics of timbre, because psychophysics is exactly about crossing this psychophysical divide of physical attributes on the one hand, the tone, its amplitude, fundamental frequency, spectrum, etc., and the corresponding sensation, loudness, pitch, timbre. And we should not confuse those. And also the logical views of perception, which propose that there's some sort of direct correspondence between the world and perception, sometimes seem to ignore that there's a complex step of information processing going on if the individual is using some sort of invariance of the physical stimulus. So there's a complex bridge of information processing going on in these two worlds. Okay, secondly, timbre is a quality and a contributor to source identity. That's kind of a commonplace. I'd like to see timbre as a bundle of auditory features. It's in the head, not primarily in the signal. There are, of course, physical correlates of that, but it's primarily in the head. And in the head, there are two things. There's the quality, and there's the source identity part. And these two things are not necessarily identical. So, for example, quality is studied by dissimilarity rating or discrimination. It's kind of captured by the ANSI definition, which just leaves it open what it is, and says individuals use timbre to discriminate or differentiate sounds. on the other hand, there's the source identity part, where this bundle of auditory features is clearly bound to a purpose, namely to identify and specify sound events. So here you would study this via recognition, identification, and categorization. Okay, and I'd like to give an example on the second part of this, so how we can study timbre as a contributor to source identity. This is ongoing work on the role of onsets or transients in instrument identification. So it's a commonplace in musical acoustics and psychoacoustics that onsets or transients are important in perceptual identification of musical instruments. But then if one looks at signals, it's really not that clear where to find the transient and where to find the onset. And when I started to think about this, I suddenly didn't know anymore what transients are and what onsets are and how people actually distinguish this. So here's a proposal, kind of my working definition. I call the onset of a tone just the first part of it, and opposed to that, the transient is really kind of what is visible as a vertical component in the spectrogram. So it's a rapidly varying fine structure, so to say, as opposed to the more stationary tonal components. And then the main questions that arise are, is the onset portion important for perceptual instrument identification? If yes, which component is important? Is it the stationary components, or is it the transient components, or is it both? And then perhaps as a third question, is there a difference between impulsive and continuously excited instruments? Okay, in order to study this question, I'm using a newly developed algorithm, and I'm very glad to announce this. I'm just returning from Edinburgh. And here we use the different types of time frequency orientations in the spectrogram to parse away the transient component from the stationary component. So I'm not parsing away onsets, I'm parsing away kind of rapidly varying fine structure, which is visible here, here, because this is not an onset, this is the return of the hopper of the harpsichord, and it's right in the middle of the signal. So I won't go into too much detail of the algorithm itself, but I just play you a couple of examples. So here's the original 3-tone signal. Oops, let me try to play that again. Okay. So here are the transient plus stationary component. So what's missing is the residual, basically. Here's the stationary component. So you can realize that kind of the onsets get a little smoother. And here's the transient component. Okay, it's not audible here. Okay. Sorry about that. Let's listen to it again. Okay, so now you should have been able to hear the transient, which is really kind of the part of the signal. Okay, because there are a couple of signal processing people here, I thought I just spend one slide on explaining the basics of the algorithm. It's a two-layer, or we depart from a two-layer L1 constrained minimization problem. So the phi and the psi operators here correspond to the synthesis operators of short-term Fourier transforms with long and short analysis windows, respectively. Of course, long windows to analyze the tonal parts, and short windows to analyze the transient parts. And then This is just a basic two-layer extension of the lasso problem. And then here is the ISTA solution, which also is a straight generalization from the single-layered case. And it uses the soft thresholding operator, which leaves the phase as it is and changes the magnitude of the coefficients. And then the ideas of the algorithm are firstly to incorporate the intercoefficient structure in the thresholding operation, which is called social sparsity. It's kind of smoothing along frequency for the transient component in this shrinkage mask. And it's a smoothing along time for the stationary component. And then the second step is to more explicitly model the complementary nature of the two layers, which is kind of just a sneaky, playing a sneaky trick on this iterations structure, departing from the original mathematical formulation, because we just observed that it works better, simply. And then the third step is to adapt the sparsity layer on the way, so to say, during the iteration, to adapt the sparsity level and not to leave it constant. And these three steps combined yield what I call iterative cross-shrinkage, and it just gave us an algorithm which, in my impression, sufficiently well separated these two components and allowed us to study the perceptual problem. Okay, and so this is an experiment we just completed. We had 10 instruments with 12 at 12 different pitches each. And then the idea of the experiment is to compare an onset portion of a tone, which is called at 0 because it starts at 0, with a middle portion at 128 because it starts at 128 milliseconds. And then we compare the stationary plus transient component at the beginning with the stationary component at the beginning with the stationary plus transient component in the middle. And there's a training phase where people hear the original sound, including feedback, whether they correctly identify the signal or not. Is this clear? So there are three different conditions in the main experiment.
Can you take the transient 128 milliseconds after it started, or do you shift it?
No, it's 128 milliseconds after it started. So it's basically the S plus T signal at this point in time, in the middle portion of the tone. So this graph might be a little confusing because it shows a piano tone which doesn't have a transient anymore at this point. But if you look at a string instrument, for example, they have still some sort of noise components, the noise of the bow, and that's what I did not want to lose at that point. But you're right, it's not clear whether it's actually discriminable at that point in time, so it might not be audible.
Can you just take 60 milliseconds out of it?
Yeah, it's windowed with a hand window. Sorry about that. So the middle portion, here I window these 64 milliseconds with a hand window, and here for the onset portion, I just use the fade-out portion of that window. It's kind of a method adopted from study by Clara Suite and coming from the Presence lab, where they looked at the different gate durations required to identify or categorize musical instruments.
So what I was fronting about was trying to work out why there's no T-only condition.
Yeah, exactly. It's a good question. Might be a nice follow-up, but I think it will all be checked. would be nice to show that T yields good identification results. I don't think it's possible. Okay, so these are our test conditions, and here are the results. Oh no, here are some signals. So at first you hear these 10 original signals. And these are the S plus T versions at the beginning. And these are just the stationary parts.
Are they in the same order?
Yeah. And here are the S plus T parts in the middle portion. Okay, so and in the experiment, the stimuli were presented in isolated way, so it was always only one sound at a time. Here are the results. On top you see the confusion matrices, and these are summarized below as a score of identification performance. And in blue you see the original training performance, so the performance on the original training sounds. And then you have the different conditions, and the thing that's obvious from the outset is that the original sounds are of course identified best, followed by the stationary plus transient components at the onset, followed by the stationary components at the onset, followed by the stationary plus transient component, the middle portion. So it seems, if we disregard for a moment all these subtleties here, it seems that the placement of the gate, so whether we are at the beginning or in the middle, seems to play a much stronger role compared to whether there is the transient component present or not. So if we go at the same position from stationary plus transient just to stationary, we have around 10 percentage points, less than that, of a difference, but much more if we go from the middle portion, if we go from the beginning to the middle portion. So that suggests that the transient components themselves are not that important. It's rather the onset information. So the structure of the stationary components in the onset that is important for instrument identification.
So you have a collection of different excitations and families, idiophones.
Yeah.
Were the fusions sort of within I guess they are within the same family.
Yeah, exactly. Yeah. Yeah, so that's something that that one usually finds, that confusions happen within families. For example, the violin and the cello are really highly confused. People had a lot of trouble with them. Also, the marimba and the vibraphone, the confusions that happen for those sounds happen within this category. So that plays a part. Regarding this third research question that I noted in the beginning, whether there is a categorical difference between impulsively excited instruments and continuously excited instruments, that's what I expected, but that's not that clear. For example, here the vibraphone shows remarkably little of an effect compared to the marimba, for example. And then again, you have also continuously excited instruments, such as the, let's say the violin here, that has a big difference between the steady state portion and the onset parts.
This is also over one note.
Sorry?
It's also over one note, right? One pitch.
It's average across 12 pitches.
And all within the tessitura of the instrument.
Yeah. Well, yeah, it's not for every instrument a perfect range, but yeah.
Just wondering whether you think the duration of the stimuli would have an effect on the performance.
You mean the duration of the gate or the original sound?
No, basically the examples that you generated.
Yeah.
Because I found them a bit short,
Yeah.
especially the middle part, because I'm kind of assuming that if you allow the air to integrate for a longer time, maybe you get better. But just assuming, so
Yeah.
I'm really asking
Yeah.
whether you think
Yeah.
it's relevant.
Yeah, it's a very good question. Of course, it is very relevant. So I'm choosing this duration because in piloting the experiment, I had the impression that's difficult enough to get an experiment that is sensitive to manipulations. Because if I choose gates that are too long, performance just is perfect and is at ceiling all the time, and then I don't have an effect of my stimulus manipulations. If you're interested in that specific question, there's a paper by Clara Süd and Trevor Aegis and Daniel Pesnitzer in JASA from 2014, which looks at this question specifically and looks at the minimal duration or the minimal gate duration required to categorize instruments into 3 different categories. And they even use sounds that are shockingly short, like 8 milliseconds, and you can tell apart the voice from string sounds. Okay. So I'd like to come to the second portion or second aspect of this second distinction, namely to the quality. This was part of my PhD. Here we were wondering what role the availability of acoustic categories plays in dissimilarity ratings. So the tentative visual analogy would be to compare dissimilarity ratings between Van Gogh with the Pollock, and one elicits categories like a church and a lake, and the Pollock really doesn't elicit many categories, at least at first sight. So we tried to generate sounds that do not elicit or quickly elicit sound source categories, although this is difficult. Our design steps for this were we took a set of acoustic instrument recordings, fed them through a Gammaton filter bank, extracted fine structure and envelopes, and then mismatched those. So we took 2 sounds, for example. We took the fine structure of one sound and combined it with the temporal envelopes of another sound per band. And then you sum all up and you get something that sounds really weird and flanging effects, but also some just really weird sounds. Then we generated a whole bunch of sounds like that and had people rate familiarity of those sounds, and thereof selected 14 least familiar recordings, transformations, combined them with 14 recordings and matched their loudness. And then people rated the dissimilarity between those sounds. So in the study there was a set of recordings, a set of transformations, and a mixed set. And here's an example for the recorded set. transformed sounds. So you will now say, oh, I can recognize this and I can recognize that. Some people, or one subject said, I recognize a frog being sled. But that's not the point. The point is really that we have a difference in familiarity. So one set being highly familiar to those musicians that we tested, another set being less familiar. Okay, and then the part of the study I'd like to talk about is the modeling part, where the question is, can sound source-based features improve a robust acoustic model? So we start from the different sound signals. We extract acoustic features, basically standard timbre toolbox features. Feed them into a partial least square regression model and fit them to dissimilarity dating rata. And then the question is, what happens if we also include categorical features about their sound sources? Does this improve performance? And here you see the performance of the solely acoustic model. So on the y-axis, so to say, you have the performance on the training set and evaluated on the test set on the x-axis. Right? So a model fitted to recordings, evaluated on recordings, achieves an R² of around 0.8. Fitted on recordings, evaluated on transformations is worse. But overall, I would conclude this is a fairly robust model, at least for the domain of timbre. Like R² of 0.8 is okay if you talk about timbre. And this is the acoustic model only. And then the question is, did we miss something? So if we look specifically at the data, we see that there are some severe outliers. So on the y-axis, you see the observed dissimilarity, so the rating score. And on the x-axis, you see the predicted similarity. And now we're considering the set of recorded tones. And here, for example, you have two salient outliers. The first one is the vibes-marimba pair, where the model overestimated similarity. And the second one is the harp-trumpet pair, where the model underestimated similarity. And the thing to note there is that these two outliers correspond to the suggestion that categorical features play a role, because the vibes-marimba pair is, of course, coming from the same instrumental family, and the harp-trumpet pair is coming from different families. And for the first one, acoustic model, just the acoustic model for the vibes-marimba pair yields a much higher predicted value than what's been observed. So this, although this is of course at this stage still anecdotal, this might suggest that categorical features play a role. So more specifically, we then also looked at a categorical model where we had 4 different variables. We just in binary fashion encoded whether 2 instruments were of the both impulsive or sustained, were plucked, struck, bone, or blowed, were coming from a string, air column, or bar, and shared the same instrument family. And only using those 4 variables we can basically achieve this or a similar score. And then if we combine those 2 worlds, then this yields the best model, which is significantly better than both individual scores. So from the modeling perspective, this suggests that people integrate their knowledge about sound source categories into their dissimilarity ratings, even without being instructed to do so. So the instruction was just rate the dissimilarity of the sounds on a scale. But they can't help to say, okay, this is a marimba and this is a vibraphone. Okay, both have some sort of same excitation. Okay, so this must be really similar, right? So this is how they integrate the knowledge about sound sources. And so regarding this distinction between qualitative timbre and timbre as a contributor to source identity, this tells us that in studying the qualitative aspect, we really need to be careful in picking our set of stimuli. So whenever there's affordance for source identification, people might actually be rating the sources and not the sensory properties that they receive. Okay, so how much time? Okay. So the third point is just an aside. Timbre is a property of fused auditory events. Just a brief remark. It could be elaborated and studied much further, but I don't have much more to say on that. So in MIR, when you consider timbre analysis, and myself, I've done similar work, you usually consider the mixture, the audio mixture in the end. And you apply timbre features to this, and then you try to come up with some sort of result. And this, of course, makes a lot of assumptions. And the assumptions basically are that the feature analysis of the mixture accurately reflects auditory scene analysis. Because when you listen to a mixture, what happens is the auditory system decomposes them, at least partially, into different streams, stream segregation, and then timbre is computed on the separate streams, right? It's not computed on the mixture of the streams. And that's why I just want to note that the notion of polyphonic timbre, capturing the overall emerging timbre of a jazz ensemble, for example, a rock concert, a symphony, as defined by Lurie and Tarvan, a great paper in 2010, is somewhat imprecise because it doesn't reflect this aspect of auditory scene analysis, right? So when we speak about hip hop, the timbre of hip hop, it doesn't mean that the fat bass drum and a snare hand clap yields one monolithic timbre. It's the kind of the combinatorial interplay between those different timbres that constitute what we mean by the sound of hip hop. It's not a single unitary timbre. This, of course, poses many problems to MIR because we would say, okay, we always need source segregation or source separation, which works really well before we do any sort of timbre analysis, which is, of course, a very difficult problem. But at least conceptually, one doesn't run into many problems when one not forgets about auditory scene analysis.
Are there any experiments on, so let's say I have an instrument recording, now I play something on top. Are there any experiments saying to which degree my capability, for example, to recognize the instrument or whatever is measurable about timbre or whatever we want to call it, how much that is affected?
You mean the perceptual identification in mixtures? No, not now, but perhaps in 1 year. I mean, this is a future project I'd like to look at. Yeah. But I'm not aware of instrument identification in mixtures. Yeah. Okay, so the last point, it actually connects well to the topic of beatboxing that we had at lunch. It's a different type of language music relation. So timbre functions on different scales of detail. The textbook definition of timbre considers, says timbre is what distinguishes a violin from a trumpet played at the same pitch and dynamics. So we have musical sounds, we have orchestral instruments, string instruments, and then they have the violin, and that's the end of timbre. But of course that neglects a whole lot of things, namely that there's a covariation of timbre with playing articulation and technique. There's covariation with loudness, with pitch. You have acoustic transfer functions involved. For example, the room, you have a whole bunch of audio effects involved, which are really important in many scenarios. And then you come to a realm which is more, which is usually called sound quality, where it's about really fine-grained details. I'd just like to mention that there are kind of different granularities by which you can consider timbre and study timbre. And so the notion of the violin timbre is therefore very misleading, because the violin timbre can generate, the violin can generate a whole bunch of different timbres. Stephen McAdams always calls it a universe of timbres, and it's exactly this size, makes this gesture. Karl Krumhansel calls it a hierarchy of embedded distinctions. And I think it's useful to not forget about this hierarchy that you might visualize with a tree in order not to get confused. So in this last empirical example I'd like to talk about, it shows a very interesting musical example where we consider timbral variety within a single instrument, namely the North Indian tabla. And here the question was, how do the different modes of tabla playing and tabla recitation, how do they tap into memory? So tabla is, of course, involves playing this pair of hand drums, but it also involves the recitation of syllables that are matched to drum sounds. Before I say anything further, I have a video of my tabla guru, Sean Madivetsky at McGill, who explains everything very quickly.
The tabla is a pair of drums from North India. It's the most common, the most popular percussion instrument from that part of the world. How we learn tabla is through this vocal language called bol, which is a lot like solfege. So as a melodic singer in the West might sing do, re, mi, fa, sol, on tabla we have these vocalizations, these bols, for every sound that we play. For example, na, tin, tun, te, ke, and ge. Then if we have combination sounds, of course we need new bols, because I can't possibly speak two sounds at the same time. So for example, na and ge gives dha. Tin and ge, pin. Te and ge, te. And then, just like letters of an alphabet, we can start to put these bowls together to create words. For example, tire kita, kita taka, tire kita taka, dha tire kita taka. Then once you know some words, you can start to make phrases. Dha tire kita taka, tak tire kita taka, dha tire kita taka, tin na kita taka. And so on.
So that was the first take of that introduction video. For us, the question was, is there some sort of cognitive foundation for bowls in tabla pedagogy? So is there, for instance, a language advantage? Is the bowl version simply easier to memorize compared to the stroke? And also, what's the role of expertise? So do tabla players simply better memorize tabla sounds compared to musicians that are otherwise matched in expertise? And the good thing here is that the expertise factor is not really confounded as usually in Western culture. So when we try to study, the differences between musicians and non-musicians, it's usually confounded with a whole lot of different factors. Whereas here we had music students who took tabla lessons and music students that didn't take tabla lessons and that didn't know a lot about tabla music, so they were pretty naive in that sense. Okay, so just briefly going through the experimental design, we compared idiomatic tabla sequences, which you can see features some sort of hierarchical structure. The question also was, what role does this structure play? So people heard these 8-item sequences, followed by a 3-second delay, and then another sequence like that. And then the question was whether the order of the second sequence was different compared to the first sequence. So here you have an example trial. The order was, of course, different in the second version. And then the second condition, in terms of the sequence structure we used, was that we just reversed the sequences. So this would retain this sort of hierarchical structure, but it would make the sequences that are idiomatic to tabla players non-idiomatic to tabla players. So it simply removes the aspect of sequential familiarity from the tabla players. The third condition was a random order condition, where for every sequence we retained the set of items, but we scrambled their order. So there you still have affordances for chunking, and you still have structure because you have repetition of items, but you don't have this sort of nested structure anymore. And then as a control condition, there was a condition where we just had randomly drawn items without replacement. And here's an example for the verbal version, so using the bowls.
Na, ka, ki, te, ha, ka, ti, re. Na, ka, ki, te, ha, ka, ti, re.
I can't remember whether it was same or different order, but it must be different order. So these are the results. I go very quickly. There is no significant difference between tabla players and musicians, which was remarkable for us at first sight. There's a strong effect of the sequencing condition. So if you go from left to right, if you remove structure, idiomatic sequences, reversed sequences, random order sequences, and random item sequences, you lose sensitivity, you lose performance to discriminating these changes in order. And then there are a whole lot of interactions. So sequencing interacts with group, sequencing interacts with material, and importantly, we interpret these results or these two interactions as being driven by this three-way interaction of the sequence, material, and group factor, which means the schema, the idiomatic nature of the sequence affects the memory for the verbal material, but not for the instrumental material. And otherwise, there's no big difference between the verbal and the instrumental material. This means only if we have this sort of, and importantly, this is only the case for tabla players. So really only tabla players who know the material have an advantage for idiomatic sequences when they are played as bowls. So we interpret this as an indication for simple word learning for tabla players, for these idiomatic sequences. They learn these bowl words, and then the nature of the verbal material allows them to efficiently chunk those sequences and better memorize those sequences. Right? So if we chunk verbal material, it's really easy to remember. Like, I mean, German language is very good at this. I think your paper at DAFX was a good example for that. Was a something with concatenated synthesis. You can just chunk a lot of stuff together, and then it's very efficiently stored. But the same thing does not happen for instrumental sounds, where it seems people more veridically store the sensory information. Okay, so this is kind of a rough summary of these results. And
were all the examples in this study as slow as the ones you displayed?
Yeah,
or did
exactly.
You
Yeah,
at different speeds?
Yeah.
Because I assume that the tabla players probably would be much better at identifying sequences at a much higher than the
Yeah, that's a good remark. Yeah, it might be a good follow-up, and then perhaps there would be a strong effect of this could happen, that you could get an effective group when you increase the speed. Yeah. I mean, this tempo is not so unusual for a scenario where you learn a new tune, right? That's what we tried to test here. Like, say you learn a new tune, is it easier if you are being presented the material verbally or just by playing? And that speed is appropriate for that question. Yeah, okay, thanks. That's about it. I'm happy to take questions.